So this is E698G. We are at lecture 9. So we saw about charge pump circuits. We saw what is meant by a drain switched charge pump. Then we saw source switched charge pump. So the next obvious topology to check would be the gate switched charge pump circuit. How do you think this topology would look like? We need to have the switch at the gate. So what are we switching in when you have switch at the gate? We switch it to VDD and then to bias. Okay. So let's say we have our up current source like this. So this is what is providing us the up current. And this is the second current source, down current source. So let me directly name them. Let's say this is M1 and this is M2. We will have the bias voltage VBP and VBN. And when we want this up current to be on, we simply turn the switch on, right? And connect VBP to the gate of this transistor. So now when we want this off, is it sufficient if I simply turn the switch off? Sorry? Okay. Does it turn the current off if it is floating? Does it turn the current off? Why not?
There will be no current who are adding. In that case, also there will be no that voltage will appear at the gate.
Okay, so another way to look at this would be that there is some capacitor associated with this node, right? So when you turn this on, this capacitor is charged to VBP. Now, if I turn the switch off, this capacitor is floating, but it still holds the value VBP. Now, of course, it's possible for this to completely leak through and eventually reach VDD such that the VSG of this PMOS is 0. But that will take a long time and we cannot rely on leakage currents for our circuit to be functional, correct? So if we want this node, if we want this up current to be 0, which means we want the VSG of this PMOS to be 0, we will have to manually do it. So we'll have to connect another switch here. Now, when do we want the switch to be on? What should I connect here? Up or up bar? So when up is high, that is when we want the current to be on. And when up bar is high, we'll want this to connect to VDD. So the same logic applies here as well. So we will have down switch connecting here and down bar switch connecting here. So this is a gate switched charge pump circuit. Now, of course, we have to replace these switches. Which portion? Up bar and up. Okay. So we want the up current to be on when up is high. Correct. So if the up signal is like this, we will want I up to be like this, where this is some I0 value. Correct. So when up is high, that is when we want this transistor to turn on. So it should get the bias voltage when up is high. When up is 0, we want this to be off, which means this has to be connected to VDD. Okay. Yeah. So now we have to replace these switches with transistors. So help me out here. What switch should I connect here? So I have 3 options, NMOS, PMOS, or a transmission gate. This should be easy, right? What switch should I connect here? PMOS, because we are going to conduct VDD. So this is PMOS. What about this voltage? Is VBP closer to ground or closer to VDD? VBP will also be closer to VDD. It will be VDD minus some VSG. It is likely to be closer to VDD than closer to ground. So this is also another PMOS. And what signal should I connect here now? So this is up bar, and this is up, simply because I have replaced the switches with a PMOS. Okay, so the same thing applies here. This will be now an NMOS. This is also getting replaced by another NMOS. What signal should I connect here? So this is down and this is down bar. Okay, all right. So now quickly tell me the range for VC. What is the minimum and maximum value that VC can take such that M1 and M2 still act as a current source? So tell me the minimum value. Sorry? VG minus VTH of 1. So what is the value of VG now? VBN, right? So this is VBN minus VTH1. Okay. And this voltage will be? So VBP plus mod of VTH2. This is clear. Now, is this range larger or smaller than the other charge pump, than the VC range for the other charge pumps? Large, small, same, similar? Feel free to look back at your notes. Larger? Does it make sense? What is causing the difference now? Drop across the switch. So earlier we had the switch in this path, right? So when you have the switch in this path, we'll have some drop across the switch. So we remove the switch from there. We don't have to worry about the drop across the switch. Therefore, we get to have a larger range for VC when you are operating. So you can characterize your VCDL for a larger range of VC and still be able to use it. Okay, so now let's look at the other non-idealities we discussed. Can you comment whether charge injection will be a problem here? If you don't remember charge injection, what charge injection is, again, feel free to refer to your notebook. Okay, somebody said no, right? Why? Okay. So charge injection is now with respect to the capacitor, right? So we have some capacitance here. So this is M1. We'll have a capacitance here. Whether some charge is getting injected to the capacitor is the question. Why?
When we turn on and off the switches, only can go to the capacitor that are at the gate. Will go through VGB or VGB.
So anything associated with the switches are not going to come here, right? Even if there was some charge within these transistors, it has a low impedance path towards the supply. So it will not flow into the capacitor. It will flow into the supply. Okay. Now, what about clock feed through? So we have a capacitance here, right? Even if you have a switching activity at this node, so yeah, even if you have a switching activity at this node, that can get coupled here. Now, for this to get coupled to the output capacitance, it has to couple through another capacitance, which would be the CGD of this PMOS transistor. So it's already a secondary coupling. Therefore, the effect is going to be much lower. Right now, one more interesting fact that happens here is, so if you are connecting the up bar here, if up bar is having a rising edge, up is expected to have a falling edge. And this falling edge will also couple to this node through this capacitance. Now, since both of them are PMOS transistors, it's possible to size them such that these parasitic capacitors have the same value. So it's possible to cancel out the clock feed through also, provided you are able to match the up bar and up exactly. Right? Now, even if it doesn't get cancelled exactly, the coupling appearing at the output will be a much, much smaller fraction as compared to the earlier cases. This is clear? Okay, so it looks like this charge pump has very nice properties, but of course, something has to go wrong, right? Then only it will become an analog circuit. So what is happening here is, it turns out the rise and fall time of the up and the down currents can be skewed by a large amount. So let us look at that. Let me name all the transistors. So M1, M2, let's say M3, M4, M5, and M6. So can you comment on the value, that voltage value that needs to appear here for M1 to turn on? What is the minimum voltage you need to have here for M1 to turn on? VTN1, so VTH1. Now, what is the minimum voltage that needs to appear here for M6 to turn on? Sorry? VT, so if down is VTH6, right. So you need to have the down signal should be greater than VTH1 plus VTH6 for the down current to turn on. Okay. Similarly, what should be the value of up bar for M2 to turn on? So VDD minus. So let me, can you, you have used 2 mod VTP. So what are the 2 VTPs? M5 and M2? Okay, so far good, right? So now you can see that the down has to be larger than 2 threshold voltages. The up has to be VDD minus 2 threshold voltages. And this is PMOS, this is NMOS threshold voltages. So now if you remember, when we learned about the process corners, we also learned about SNFP and FNSP process corners. So this stands for slow NMOS and fast PMOS. So this means that the VTN is going to be large value because it's going to turn on slowly, and VTP is going to be a small value. And this will have the reverse scenario, fast NMOS, slow PMOS. So now depending on whether your chip, your die is coming in SNFP corner or FNSP corner, the up and down currents, the rate at which the time taken for them to turn on is going to be very different. For example, if your chip came in SNFP corner, which of the currents is going to turn on faster? So I up is going to turn on faster than the down current. Okay. Now, if it came in FNSP corner, it will be the reverse. Now, you can't design for all corners together unless you think of a special algorithm or special calibration circuit or some feedback, right? Without that, if you are just designing, our best approach would be to design for TT corner and then simulate and verify that across all the other corners, the performance is acceptable, right? So it would become a little harder to meet the, to make sure that the switches turn on at the right time between SNFP and FNSP corners. Okay, so this is one minor drawback with this circuit. Okay, so now, as we mentioned earlier, if there is mismatches between, switches turning on, what we expect to see is some variation on VC, right? So the charge pump is going to push charges onto a capacitor. So even under steady state, our capacitor voltage, instead of becoming a steady voltage, it will have some ripple. That ripple is periodic from one period to the next, which is why we call it a steady state. Now let us, and I kept telling that it is not desirable, but let us see why this is not desirable. what do you think will happen if I have a ripple on the capacitor voltage? How does it affect our output? So we are finally interested in what the VCDL is going to give us, right? So this is the output that we are interested in, and this is connected to the capacitor. Ideally, we would have liked our VC of t within one period to become a stable value like this. But now it's going to start at some value, could have a ripple, and then we'll end up at the same value. And this is then a periodic waveform. So what do you think is going to happen? So let me give you a counter argument. You're saying that the TRF is going to vary, right? But we already said that this is steady state, right? So if you look from one period to the next, we know that the VC is the same. So TRF also has to be same, right? Otherwise it is not steady state. Rising and falling edge can be distorted. Okay, so to understand this, let me first give you a very simple example. Let me take a buffer. Okay, now this buffer delay is controlled by VC. So if you are using current starved inverters, to put current starved inverters and you have a VC. Let me assume that the input given is a stable VDD. The output will also be a VDD. Correct? Now let's say I vary this VC from 0 to VDD. Does anything change with respect to the input and output? Nothing changes? Is this okay? Is this fine? I see a lot of confusion. I'm varying the delay of this buffer, right? But if the input is a constant, output is also a constant, we won't see any difference, right? Now, instead of this being a constant, let's say I give a rising edge like this. Then I expect to see a rising edge at the output. Now, the position at which this rising edge is going to appear will depend upon the value of VC seen at that instant, right? So this VC value matters only during a transition. Now, this is true if I have a rising edge at the input or a falling edge at the input. This is clear? Okay. So now let us look at our VCDL as a whole. So let's say this is my in. I'm calling this N1, N2, N3, etc. And then finally the out signal. Let me sketch out a VC waveform. So this is for one period. Let's say my in is like this. Now N1, let's say I use a delayed version. N2 is this. N3 is this, etc. Now, finally, out signal, depending upon the VC waveform, it may or may not lock with an offset. So let's say out has locked with some offset, and we have it as shown here. So this is steady state. It has just locked with an offset. Okay. So now what is happening is the delay of each of these buffers will now depend on the value of VC when the rising edge is occurring. This is true for both the rising and the falling edges. Now, all of these edges are going to see different delays depending on the value of VC. So ideally, we would have expected this to be some TRF by N. Okay, so this is assuming that this whole chain locks to TRF and that there are N elements. So the whole chain locks to TRF, and if there are N elements, the delay of one buffer is Tref by N. But right now, because let's say VC has increased, then we would, in a current stopped inverter, we would expect the delay to decrease. So this edge is now going to move ahead. Right? Now, if this edge has moved ahead, that means the rising edge going to the next buffer has moved ahead. Therefore, its output will also move ahead. So this is one effect. The other effect is now at the instant where this edge is supposed to happen, we have to check the value of VC. Now, depending on that, this delay can further increase or decrease again. Okay. So now this is going to happen with all these edges. Right? But this change will be a constant from one period to the next, because every time it is going to sample the same value of VC. Okay. So we will have a steady state error in the phase difference between these rising edges. We will also have a steady state error in the duty cycle of these edges, the duty cycle of these pulses. Okay, it's clear. So the effect is the duty cycles will vary. The phase difference between any two edges will also vary. And all these variations are steady state variations. It doesn't change from one period to the next. It remains constant. This is okay? Okay. So now we have to, so we know that if there is a variation in VC, we have all these problems. Now this may or may not become a problem depending on the final application that you are working with. If you are only interested in the edge of in and the edge of out, what happens during the other rest of the period to VC may not be of a concern to you. Okay, but let's say we want to reduce a ripple in VC. How can we change the loop parameters such that we can reduce the ripple at the output? So finally, we are interested in the ripple at the output edges, right? So how should we choose our DLL parameters such that we have minimum variation at the output? So what are the loop parameters that you can think of? What all does our loop have? We have a charge pump. So the current of the charge pump is one parameter that we can set. So ICP. Then we have a capacitor. So what value of capacitor we should choose is another parameter, right? Now, if I look at my VCDL, this will have some characteristics of TP versus VC, right? And it will have some curve like this. Now, the slope of the curve is also an important parameter for us, right? Because if I have a small variation in VC, by how much does the delay change? And this can be captured in the parameter KDL, the gain of the delay line, right? So now to reduce variations at the output, how should I change these parameters? Should I increase them, decrease them, or they have no effect on the output? KDL should be small. Okay, that is very obvious. C should be large. Why should C be large? So is there a general
that is not sufficient for that.
So can you generalize this? So what all of you are telling is correct, but is there a generalized statement? So let me simplify it even further. Let's say I'm looking at some ripple on the capacitor. This delta V will be equal to some delta Q by C. Now, if C is larger, for the same amount of charge, I will have lesser ripple. Right? So the answer you gave is all right. I'm just simplifying it a bit further. So we would prefer to have a larger C if we want to see smaller change at the output. What about ICP? Right. So for a delta T error or a phase error between in1 and in2, the charge that is getting pushed into will be ICP into delta T. So for the same delta T, if my ICP is smaller, this delta Q will be smaller. So if I want to have lesser ripple on the VC, I have to reduce this ICP, right? Now, the other problem is what you mentioned. Now, all of these things, the change that we have made here, all of them are going to increase the locking time. It is going to take more time for us to reach to the final lock point. Okay, so this is actually, I'm slowly bringing you into this concept of tracking bandwidth. That is, also you can think of it as small signal bandwidth. If I have some smaller variations in your circuit, how should I adjust these parameters such that I can track it faster or I can track it slower, right? So we will see more details about this when we deal with a small signal phase domain model of the delay locking. Now, before I get into that, let me also look at the mismatches and the problems mismatches can cause in a circuit. Now, we talked about mismatch earlier when we discussed about the property variation within the die and in between the dies. So is mismatch an intra-die variation or inter-die variation? Intra-die variation. Yeah, so this is the variation in the transistor properties within a single die. If you are looking at variation between one die to another, then we call it as process corner variation. Within a die, we call it as mismatches between the transistors. So this is intra-die variation. So let me quickly sketch out the drain switched charge pump circuit. So this is a bar. We have a reference current. This gives us VBN. So I'm going to generate VBP using an op-amp. This should be connected to ground. Should be connected to VDD. And then we generate using an op-amp. So this is VBP. So now the op-amp will ensure that these two nodes are VC, right? Which means that the transistors on both sides, so these two transistors will see the same voltages as these two transistors. Therefore, the current flowing through them will be equal. Okay, so same happens at the bottom transistors as well. Now, this is true, assuming that the transistor properties are the same. What if this transistor had VTH1 and this had VTH2, where VTH1 is not equal to VTH2? Then the current mirroring will not be exact, right? So if I were to, so this is a problem throughout. Similarly, these two transistors need not have similar properties. The up PMOS transistors also need not have similar properties. If this happens, then we will have a current mismatch. And this current mismatch is not exactly predictable. We don't know the exact value with which the current is going to be mismatched. Now, this is different when we had VC being different, the VDS of the transistors being different. If we know what is the difference in the VDS, which we can find out from simulation, we will be able to exactly predict by how much the currents are mismatched. This is different. So this is due to random mismatches in the transistor properties. And this being non-deterministic, we will now have to deal with statistics, right? Statistics of by how much the VTH is going to vary. So if I take one more example where this mismatch is relevant to you is within the VCDL. Now we said that if I take n VCDL units and ensure that the total delay is some Tref, this will be equal to Tref by n. Right? This is true only if the n buffers are identical. if they have different transistor properties, maybe the mu is different, VTH is different, what will happen is we would expect it to have Tref by N. Okay, let's take the ith buffer delay. We would expect it to have Tref by N, but instead it will be Tref by N plus some Ti, right? And all that the DLL ensures is that summation of all these buffer delays, which is summation of Tref by N plus Ti, where Ni goes from 1 to N, this is equal to Tref. Okay, the DLL is locking the total delay. It is not giving us any guarantee about the individual buffer delays. So if you have mismatches in the transistors, you can have different delays for these buffers. And in applications like a time to digital converter, this is a problem because we were relying on the delay of a buffer being completely known. Okay. So now if I take a transistor, the properties that can vary are mu, COX, VTH, W, and L, right? Now, all of these can vary. Now, I have written W and L also here. So you should be asking the question, isn't this what we decide? As designers, we put in the value for a transistor width and transistor length. But it turns out this is not completely under our control. We can give a nominal value, but during fabrication, there would be microscopic variations in the width as well as the length of the transistor. Okay, so let me write the equation for current under saturation region. This is half mu and COX, W by L into VGS minus VTH, the whole square. The variation in all these properties, we will represent this as a relative mismatch. That is, we are looking at it as some delta beta divided by beta. Okay. Now the variation in VTH, we usually deal with it in terms of absolute mismatch. And this is some delta VTH. So if I were looking at this VTH parameter, it will have some mean value and some sigma value. And we are interested in how much this standard deviation is, right? The mean is fixed by the process corner. If you say it is in TT corner, we expect to see some mean VTH. But even on the die, it is going to vary around this mean, and that we quantify based on the sigma VTH. So you should be asking me a question now. Why are we dealing with beta in terms of relative mismatch and VTH in terms of absolute mismatch? Now, since you are not asking, I am asking you the question back. So in all these calculations, what we are finally interested in finding is how much my current is going to vary relative to the ideal value, delta ID by ID. Now, if I give you delta beta by beta, you can calculate this directly because this beta is appearing as a proportionality constant, right? But if I give you delta VTH by VTH, it's not so easy to calculate because you have to subtract it from VGS and then take a square. So that is why we deal with VTH in terms of the absolute value and beta in terms of the relative mismatch. Okay. So the general thumb of rule is that if you increase your device area, the mismatch is going to reduce. Okay. Now I'm going to give you a small flavor as to why this is true. We will not get into the detailed calculations, but let me show you that with a small example with respect to W as well as length. So let's say I'm looking at the parameter delta W by W and delta L by L, right? If I increase my W, it's quite easy to see that this parameter is going to reduce, right? So in other words, my current is proportional to W by L. Now with with these variations, instead of W by L, I can write it as some W into 1 plus delta W by W divided by some length into 1 plus delta L by L. Okay. So if I increase my W, you can see that this numerator is likely to tend towards the ideal value we expect. Okay. But why should the variation of delta L by L also reduce when I increase my W? The question is clear? Okay. So let me show you why that can also happen. So I'm going to take two transistors. Let's say the first transistor has a width of W and a length of L0. Okay. So this has some W by L0. Now I take another transistor. This has the same length L0, but its width is much larger. Let's say the width is N times W. So I'm looking at another transistor with NW times L0. Now I can model this as N parallel transistors with same W and L0. So this is my first transistor. This is my second transistor. And I can have N such transistors. Okay. And then I'm connecting all of this together. So they are equivalent. So here all that I've done is I've taken one transistor which has W by L0 as the size. Now I have cascaded N such transistors. And all their drains are shorted, all their sources are shorted. So if I were simply looking at the voltage and current relation, both of these will have the same current. Okay. So now let's say, just to keep things a little easier, I'm going to call this as a random variable L1. This will have a length of, let's say, L2, etc. So nominally, everything is L0. So to make the calculations clearer, I'm using these variables. Now, I could say that the equivalent length of this transistor is the average of these individual lengths. So equivalent length is simply L1 plus L2, etc. plus Ln divided by N. Okay. What comment can I make about its standard deviation? So these are independent random variables, and I'm finding the average. So if I were to look at the standard deviation of this equivalent length, it will be sigma of L1 square plus sigma of L2 square plus etc. up to sigma of Ln square divided by N. So this is equal to, now let me replace L1, L2, Ln etc. with L0. So this simply becomes equal to L0, right? This becomes N into sigma of whatever was the standard deviation associated with the transistor with length L0 divided by N. So this gives us sigma of L0 square. Yeah, I'll take the root as well. So this divided by root N. So just by increasing the width N times, I got a 1 by root N advantage in the standard deviation associated with the length. Okay. So the general expression for this is, so let's say sigma delta beta, this is given by some proportionality constant divided by root of Wn. Similarly, sigma VTH, now how you represent the notation, you will have to check every time you come across this notation. Some people use it as sigma delta beta by beta. Sometimes it is just sigma delta beta, and sometimes they use sigma beta also. So anytime you come across the notation, just check the definition once. So sigma VTH is some proportionality constant divided by root of W into L. So anytime you want two transistors to be matched, the first thumb of rule is increase its area. You have to figure out whether it is best to increase the width or the length, but increase its area and you can bring down the mismatch between the two transistors. After you have done this in the design, when you do the layout, you lay them out identically. You make sure that they see the similar environment, etc. But all that you will learn in, I think in 613, you should be learning all these principles. Yeah. Okay, so now let me come back to our charge pump circuit. How many of you are doing 613 this semester? I think high frequency analog design course. So if you are interested to learn more about this and you happen to not be registered for 613, this is a very good reference. In IEEE circuits, you look for process variation and Pilgrim's law by circuit under circuit intuitions. So this is a magazine by Solid State Circuits magazine, and they have this section, tutorial section going on circuit intuitions. So this is a good reference to look up. Okay, so let's get back to our charge pump circuit. Now we want to match, say, these two transistors. So we have two choices. We can increase width, we can increase length. What should I do? Increase width? So let's talk about the length first. Should I or should I not increase the length? Correct. So this is a current source, right? And we would have liked this current source to be less dependent on its VDS. Now, if you increase the length, the effect of channel length modulation decreases. So for current sources, it's very common to increase the length. And then on top of it, if you want, you can increase the width also. So if it's a current source, you are free to increase both width and length. And there are benefits to increasing the length as well. And width you can choose depending upon the current you want in your circuit. Okay. What about the switch? So again, let's talk about length. Should I or should I not increase the length? No. Capacitance will increase. But if I increase width also, the capacitance will increase. So you can think of it in multiple ways. One is if you increase the length, the drop across this transistor is going to increase, which means the range of VC available to you is going to reduce smaller and smaller, right? Whereas, so the other way is to think about it in terms of the effective on resistance. You increase the length, the effective on resistance is also going to increase, right? Whereas if you increase, so increasing the length is generally not preferred, but you can increase the width. It is going to reduce the drop across the switch, and you can take care of mismatches. Capacitor will increase, right? So, but the hope is you increase the capacitance, but you're also increasing the current. You will have to increase the current that can flow through this using this. So it is still possible to get around it. But so there are benefits to increasing the width, but with length, I think the trade-offs are not in favor of increasing the length. Okay. What about a buffer? So if I take a VCDU unit, so voltage controlled delay unit, again, I have the choice of increasing the width as well as the length. What would you prefer? This is sort of a trick question because it actually depends on how you implement. But in general, we tend to increase the width more than the length. Because if you have already designed for some delay, if you increase the width, you are likely to be within the same delay ranges. This is assuming self-capacitance and the load capacitance are roughly equal. If you increase the width, your self-capacitance is going to increase, but the current flow is also increasing. So you might be able to maintain the delay within the same ranges. But it really depends on the implementation. So I cannot rule out either of them, but generally width is increased as a first choice. Okay. So now almost everything you implement with analog circuits are custom designed, which is why I cannot give you an exact answer. I keep saying generally, usually. The actual trade-offs you will have to see during implementation and then decide for yourself. Okay. So then let us move on to the delay lock loop circuit completely again. So we have seen VCDL, we have seen PFT, we have seen charge pump implementation. Only a capacitor is remaining, but everybody knows what a capacitor is. The only additional information I can give here is this is also called as a loop filter. So this is contributing to the integrator action, which is basically an averaging filter. So it's called as loop filter. And in practice, it need not be a single capacitor. You could potentially put a complicated loop filter in this place. Okay. And then we were looking at, so we sort of touched upon the topic of how our choice of charge pump current, capacitor value, the characteristic of VCDL, etc., are going to affect how effectively we are tracking the changes at the reference. So the next order of business is to model this in some small signal model, right? So into a sort of model that we deal with when we are dealing with amplifiers, so that we can do quick hand calculations, look at its bandwidth, etc. So first of all, should I model this as a continuous time system or a discrete time system? The question is clear. Is this, so if I were talking about a regular amplifier without any switching, we know it is a continuous time system. At every node, the voltages can take values continuously, right? Now, what about this? Is it continuous or discrete with respect to time? It should be continuous. Why? Huh. Correct. So his argument is that we have the voltage on this capacitor is free to vary continuously with respect to time. If you look at the signals, these are also continuous waveforms with respect to time, right? Is there an argument in favor of discrete time system? So we can calculate all for so that argument is not, it's not completely correct. I won't say it is incorrect. So the reason is there will be minor variations in the reference signal. There could be variations. There could be noise in the circuit occurring at different points. So you generally need this feedback loop continuously active to make sure that this is continuously locking to reference, right? Otherwise, it can deviate from that point. But there are circuits where you turn off the feedback for some time. So then the circuit is in open loop. But then you have to periodically switch on the negative feedback so that it comes to the correct point, and then you can turn it off again. So there are certain negative feedback systems where the feedback is not continuously active, right? But for now, we will assume that the feedback is continuously active. And on top of it, I'm asking the question, does this circuit also exhibit any discrete time behavior? So let's look at the, yeah. So VCDL, we earlier saw that the VC value matters to VCDL only when there are rising edges in the system. Right now, VCDL, of course, has multiple buffers. So multiple rising edges are of a concern to us in some cases. but it still has some sort of sampled behavior. Now, the best example I can give for the discrete time behavior of this is the PFD itself. This PFD identifies a phase error corresponding to the rising edges, right? It is not detecting the phase error continuously. So effectively, I could say that with respect to time, for every period, I have some phase error. So maybe the phase error has some value. At 2 Tref, the phase error has a different value. 3 Tref, it has a different value, etc. Now, corresponding to this error, I will have some delta Q flowing into the capacitor. So these are also now discrete time values. So I can potentially model this circuit as a discrete time system also. Now, all this confusion is happening because this DLL is actually a hybrid of both continuous time and discrete time systems. So there are parameters that are purely continuous time in nature, but there are parameters, there are blocks in the circuit that are discrete time in nature. So we can potentially model this either as a hybrid model, but then it will get too messy and it becomes harder to deal with it as designers when you solve it. It is possible to model it, it has been done, but for quick hand calculations, it's easier to stick to one of the models. So this can be modeled as a continuous time model, in which case you will be looking at Laplace transforms and Laplace domain blocks. If you model this as a discrete time system, what will you use? Z-trans. So all these models are available for DLL. You have the Laplace domain model, you have the set transform domain model, and you also have hybrid models. So in the next class, we will look at how we can do the continuous time model for the DLL.